Hello everyone. A couple of administrative items before we get started. Due to the large number of attendees, we will be muting everyone's microphone during the session. You can type questions in the questions pane located in the control panel. I'll answer some questions at the end of the session. Also, feel free to send us comments about the webinar or additional questions to webinars@csiamerica.com. Also, all webinars will be recorded and posted on our website. Okay, I'm going to open up ETABS here. Okay, so in this example, I'll talk about modal load cases. I'll define a response spectrum function and a response spectrum load case and all of the parameters associated with it. Then we'll take a look at some output, including mode shapes, diaphragm acceleration, and participating mass ratios. Okay, we have a 6-story structure here. We can take a look at it here. Rotating around, you can see our DirectX has been implemented here as a default in ETABS. Just a quick overview of a response spectrum before we get started. So response spectrum analysis are typically used for performing seismic analysis. Calculates the maximum response values in each mode of the structure from a spectrum curve, and then combines the responses using modal superposition. There could be code spectrum used to illustrate a range of earthquakes, or spectra for an individual specific earthquake. The spectra curves plot period versus acceleration and contain multiple curves for different damping values. Response spectrum, it calculates the likely maximum response of the building when subjected to the pseudo acceleration of a response spectrum curve. So before we get started, let's go ahead and we'll define a modal case prior to defining the function itself. So, and we'll click on Modify Show to see the case here. Building response is not made up of a single mode, but the response of many modes. So you must combine these modes by using a square root sum of the squares method. This results in all values being positive. So, and we'll get into that once we define the response spectrum function and load case in detail. Okay, so what we have here is the modal case data. First, you need to select whether you want to use eigen or Ritz vectors. Eigen are free vibration modes, where Ritz vectors are load-dependent vectors. Ritz vectors, they're typically a better choice when doing modal superposition, and I think we'll use that for this specific example. Ritz vectors are recommended for response spectrum because this formulation is computationally efficient. Only pertinent mode shapes which occur in the horizontal plane are identified. And eigenvectors, on the other hand, are useful, or they use the full stiffness and mass matrices, which also account for vertical modes. So eigen formulation is useful when considering, say, floor vibration, out of plane vibration of say, shear wall systems. So eigen application is also useful for locating model errors. So we can use either eigen or Ritz. We'll use Ritz in this example. So we have mass source, which is defined. It defines the mass of the building. It could be defined to include other items like equipment mass as well. So once we define this modal case, I'll click over to the mass source and show you how to define that as well. P delta settings. ETABS allows for the stiffness to be used in creation of the modes to be updated by P delta or nonlinear analysis. We can take a look at Modify Show. For this model, we'll use the non-iterative based on mass automation method. But you also have the option to define based on loads, and you can enter in the load patterns here below in this dialog box. So under the loads applied portion of the menu, program can calculate static correction modes, which is imperative when modeling supports that are very stiff. Okay, I want to select eigen to discuss these other parameters here. So you can specify the maximum and minimum amount of modes here in ETABS as well. The spawn spectrum analysis will use these modes that are found. So this model that we're using here today has rigid diaphragms, so we want to have vertical excitation. So there will be 3 mass degrees of freedom per floor, perhaps 2 translational and 1 rotational. So 6 modes should be sufficient for this to capture the response that we're interested in this model, but let's just leave the number of modes as 12, which should be adequate. So there are some other parameters included here. Frequency shift. So this is to shift the search for modes to look for higher frequencies. Some things, or since this analysis is for seismic loads, the lower frequency modes are important. So we'll use, for this model, the default of 0. Convergence tolerance. So this calculates how close successive eigenvalue iterations need to be before ETABS can move to the next mode. And for this specific model, we'll leave the auto frequency shifting on. This typically speeds up the analysis and improves accuracy. Okay. So once we've defined the modal load case, the next step would be to actually define the response function itself. So we'll find that under the define functions and then response spectrum. So you'll see here there are many different codes that have been embedded here in ETABS to choose from, including many international codes. For this specific example, we'll go ahead and click on the ASCE 716 code and click Add New Function. So we'll give this code a name, ASCE 716 perhaps. We have some parameters here, spectral acceleration, S sub S, as well as S1 values that can be entered in. Long period transition period can be left here as 8. I'm going to be clicking on site class C, which is typically used for dense soils and soft rock. Here we have the points of the curve. The period is shown in the Y direction, and the acceleration in G units right here. You can move the cursor over the graph to obtain the coordinates for any point. So based upon the values that are entered here, the calculated values for the response spectrum are automatically calculated here on the left-hand side. Now you can convert to user-defined. If I click on this, you'll notice that all the values will be embedded automatically in ETABS. And this is easy for when you're sending models to perhaps clients. You don't have to include an additional response spectrum file. It's been automatically embedded here into the ETABS program file, the EBB file. Okay, so now the response spectrum function has been defined. So now we need to take some time to define the response spectrum load case. There are many parameters in here that need to be discussed, so let's get into that. So you'll find this under the define load cases. And if I modify show a response spectrum, you'll see under load case type there are many items to choose from. We'll of course select response spectrum for this example. So what we're going to do is apply a response spectrum in the U1 and U2 direction. We'll apply a scale factor. Now this might be to convert from G units to inch units or to apply code factors such as R over I. For this example, we're working in kip inch units. That's why the scale factor is going to be 386.4. If I were working in feet, perhaps it would be a 32.2. So now I'll select the function, which has been defined as ASCE 16. Now I'll go into a discussion as to why I'm applying accelerations in both the X and Y direction for this specific model. There's a certain reason for it. After I define the load case data, we'll get into that. So I can click on the advanced button here, checkbox, which allows the user to adjust the angle at which the response spectrum function is applied. Okay, for other parameters, we've defined our modal load case, so we'll leave that as is. You can, of course, define multiple modal load cases, but we only defined one for this specific model. So modal combination method. You can see there are many options available here to combine the modes for a given direction, including CQC, square root, sum of the squares, absolute, general modal combination, and a few others. So we'll use the complete quadratic combination here for this example, the CQC. If we wanted to include rigid response, the amount of rigid response and periodic is to be interpolated between the F1 and F2 values. I'll check this box here, and F2 must be greater than F1. We won't use this here today, but this option is available to the user as well. So for directional combination type, now remember, we're applying accelerations in both X and Y directions in a single load case. So we need to specify how to combine these responses. So using one of these options today, we'll use the square root sum of the squares. Okay, let's talk about why I decided to define response spectrum accelerations in both directions. So the codes sometimes require that members be designed for 100% of the seismic load in one direction, and a smaller percentage, say 30, 40% in an orthogonal direction. So to perform this correctly, it assumes you know the critical direction of the earthquake motion, as well as the principal axes of the building. So in ETABS, by using the function in both orthogonal directions and using the SRSS, or the square root sum of the squares method for directional combination, the maximum may be captured using a single analysis run. Okay, so also we have modal damping that can be defined. We'll leave this as constant as 5% for each one of the modes. Just going to bring up so our analysis reference manual has, of course, lots of information regarding all the differences between the directional combination types. It has, here I'm showing modal damping, modifies the shape of the response spectrum input curve. and all the parameters associated with this and the definition, of course. So we're going to be using constant 5% damping for all modes. But of course, you have the ability to apply specific damping values for different modes. Okay, so we've taken the time to define a modal load case, a response spectrum load case. We've actually defined the curve itself, applied the curve as an acceleration in the x and y direction. So why don't we go ahead and run an analysis and take a look at some output. So to do that, we'll go to Analyze. You can click on Set Load Cases to Run. You can pick and choose which specific cases you wish to run. What we're interested in today is the modal and this is called L case 1. I should have given it a different name, but that is the response spectrum load case. So we've selected those to be run. This just takes a second. Yeah, I like using that because, of course, for specific analyses, it saves reduces the runtime quite a bit, especially for larger models and dynamic analysis. Okay, so the first thing we'll take a look at are some mode shapes. So by default, the mode shape pops up for mode 1, and the period is shown here as well. I can use these arrow buttons on the bottom right-hand portion of the screen to step through the modes to see how the building is responding. So here's a couple translational modes. I think should be in the first 3. And once we get to a rotational mode, I'm going to start the animation. Here's mode 4. This looks like rotational, so why don't we take a look at this. Of course, the deflections are amplified drastically. This just takes a second to load. So after we take a look at this, we'll take a look at a deflected shape. I'll show you how to view output using the tables, as well as joint displacements, diaphragm accelerations, and the very important participating mass ratios. So hopefully that's coming through. You can see the rotational mode here, mode 4 with a specific period. We can also, under the display menu, we can look at deform shape. For modal, we could take a look at for a specific load case. L case 1 is, of course, the response spectrum that we have defined. Oh, scale factor seems a little out of whack. Let's click on automatic. So response spectrum deflected shape, it's a single response based upon superposition of the modes. We could show the animated shape here as well. You can put the cursor over a specific joint to view deflections, or simply right-click on a joint to get more detailed information about the point displacements. Let's look at a specific elevation, and we'll take a look at some moment diagrams as well. I'm going to turn off the extruded shape. Go to Display, Force Stress Diagrams, and then take a look at frame forces. again, putting the cursor over the element to get values, as well as right-clicking to get shear moment diagrams. And of course, these can all be printed to a nice report format as well. Okay, some important things to check when it comes to response spectrum can be found underneath in the tables as well. That's another way to view output. So if I click on Display, Show Tables, now I'm interested in perhaps taking a look at joint displacements, diaphragm accelerations. These have been all pre-selected here. We'll also take a look at participating mass ratios. That can be found underneath the structure output modal information. You can see modal participating mass ratios as well as response spectrum modal info. So I've selected a few of these items. We can click OK. And now these items are populated in a nice tabular format. So diaphragm accelerations, these are important for occupant and equipment studies. You can see for a rigid diaphragm, L case 1 is our response spectrum function. You can see the diaphragm accelerations are all displayed here in the UX, UI, UZ directions as well as the rotational. So it's also important in taking a look at joint displacements. Now you'll see here, when you're looking at displacements, all the values are positive. So this is due to how the model results are combined. All deflection values are going to be positive for response spectrum. So you can see here it's listing actually all of the labels themselves on the left-hand side, and you can scroll down. What I like to do is actually select a few nodes manually, and there's an option in the Display Tables tool where you can have it show information just for those selected items, or in this case, points. It'll reduce the number, the amount, or the volume of the information given here in the tables. So when it comes to modal mass participating mass ratios, so this denotes how much mass we've utilized in our analysis. The summation of the UX and UI should be very close to 1. So, and that's the case here. So if we'd somehow only selected 6 modes, which we were considering initially, it would only have gotten 93% in the X direction and 91 in the Y. So with the addition of the additional modes, you can see it's much closer to 1. I guess we bumped it up to maybe 16. It would have reached 1 all the way. Response spectra, modal information, damping ratios, all the periods associated with the modes can be viewed here. Accelerations, amplitudes can be viewed in this table as well. Okay, oops. Why don't we field some questions here? So yes, this video will be recorded and posted on our website. So also, any questions I don't get to here today, we'll answer them and post them on the website as well. Okay. Okay, so what value scale factors should be entered in the definition of a response spectrum load case? So when the curve is defined, acceleration is typically entered as a fractional of the gravitational acceleration. As I was saying, 32.2 feet per second squared. We were using inches per second squared. That's why I used that 386.4. So the scale factor should be specified in the response spectrum function definition, as well as the response spectrum load case definition. Okay, how is response spectrum analysis applied only above grade? So during response spectrum analysis, the loading is applied to the entire structure, though subgrade modes will have higher frequencies, but it will be providing minimal contribution to the modal response. However, mass participation of subgrade levels could be subtracted from the total mass. Okay, so let's go back to there's a question about diaphragm eccentricity option. So if I go to define load cases, response spectrum, diaphragm eccentricity. So I could define a different eccentricity on every floor. So if I click on add, so I have two diaphragms which are defined here in the program, rigid and semi-rigid. And I could define them on any one of the, let's see, it looks about 6 floors with a roof and a penthouse roof. So I can individually define the eccentricities. Now, you need to be really careful here. This is not a percentage of the length. This is an actual value. You can see here it says in feet. So you can't just write 0.05. It's not going to be a percentage. You need to actually enter in the specific value. So if I wanted to put in, I don't know, I'm just guessing here, 2 feet, you need to put in the value. So I can go in, add different eccentricities for every specific story. This only has rigid diaphragms in this model. But of course, you need to be careful. The penthouse roof is going to have a different eccentricity, say, than the 6th floor because of the different dimensions of the floor itself. Okay, so there's a question about RITS analysis. Let me talk about that again. That's an important topic. So if we go back to define modal cases, so what I was saying before, RITS vector, they're recommended for response spectrum because this formulation is efficient. Only pertinent mode shapes which occur in the horizontal plane are identified. You're asking about RITS vectors, but eigenvectors use the full stiffness and mass matrices, which account for the vertical modes. RITS are better choice when doing modal superpositioning. And I'll post a reason for the specific detail as to why on the website here after the session. Okay, so well, thanks everyone for joining me today. Again, the video will be posted on the website today, as well as maybe 10, 12 of the most commonly asked questions in the questions pane will be answered and posted. Again, feel free to contact us or make comments about the webinar at webinars@csiamerica.com. Again, thank you very much for joining me today, and please check the website for future webinars. We'll be conducting many more this year. Thank you very much.